Good morning, everybody. Let me quickly introduce myself a little bit more. So I'm a product manager at Fortify. So you might know Fortify is one of the SAST tools of the world. It's now part of Open Text as a company, but almost nobody knows that company, but people do know Fortify. That's gone through many companies in the past. This talk will be about some of the topics that are on our minds and the things that are in our lab, but it will not be about Fortify. It's in no way a product pitch. I will be here for the rest of the day. If you want to talk Fortify, obviously I'm more than willing to do that. That's not the topic of this talk. I want to show you a couple of slides to introduce the topic a little bit before going to the meat of it. So it's about the intersection of SAST and everything is code. So I guess SAST, given that you're an OWASP audience, many of you would be familiar with that. Who's using SAST tools in some way in their daily life? So SAST is static application security testing, right? So it's defined by testing an application for its security aspects without actually running it. That's why it's called static. If you look at why are people doing that, well, because you have many applications nowadays in most organizations. Security is important. The manual reviews are just not an option. They don't scale well enough. If you have 100 applications, you release them every week, and then you have 5,000 roughly release moments per year. You cannot possibly hire security experts to review all of them. So you want to automate. There are many companies that have some offerings in this market. To the right, I've listed their own vendors from the latest Gartner and Magic Quadrant on the space, and some of them are present here today as well. So that's SAST. If you look at everything as code, right? So the thing here is that code historically has been associated with applications. But now with everything as code, many other things are becoming code as well. And infrastructure is a very prominent example of that, right? Infrastructure is code, which you generally use in the context of cloud transformations, because clicking your cloud infrastructure together through a graphical interface is really a poorly repetitive, poorly manageable process. So instead you encode your infrastructure in files and then you execute that. There are many more examples of that same trend. So one thing we're going to look at is contracts as code in the context of getting contracts on the Ethereum blockchain and having contracts being executed fully automatically. There are also CI/CD pipelines as code, right? In GitHub, in GitLab, and Azure DevOps, also in modern versions of Jenkins, where your build processes become code. All of these things have security aspects as well. If you think about what is that everything as code, to define the topic a little bit better, but in its most basic way, it's about having files that can both be read by a human, by the programmer of the code, and can also be executed on some system automatically. But if that would be your only definition, then all of a sudden the entire etc directory on the Unix system would be like infrastructure as code of all networks. That's nonsense. There are a couple of more things that are specific about everything as code that will influence the security of that as well. So it's we're talking about specific languages rather than some generic scripts that define infrastructure. It's about the availability of programming constructs, right? If it's just data that configures something, that's not really something as code, it's just data. Everything is code and infrastructure is code, you're going to see that there are programming constructs. And wherever there are programming constructs, there are opportunities to use them in the wrong way, in such a way that your program becomes vulnerable, right? And that's where SAST comes in. Usually infrastructure as code is, or everything as code is also combined with code management practices, so that code will be checked into GitHub repositories so that you can do change management. And in many cases, everything as code uses declarative code as opposed to imperative code, and that makes a huge difference in terms of how you analyze it. I want to start with one motivating example. It's not the example that we're going to look at in more detail, but it gives you a good flavor of why we're looking at this example. So this is an example of a vulnerable piece of GitHub workflow code. This is not my example. I've taken this directly from the GitHub website, who have documented this extensively. So you see here a piece of GitHub workflow code, which is YAML code ultimately. So it has a YAML stanza here with a name and a run. And in run, you can define a bash script. So whatever is in the value of run, a multi-line string, will be executed as a bash script. Now there's something special here. In that bash script, you have that syntax on the third line, which has the $sign and the two curly braces. That's not bash syntax, that's GitHub workflow syntax. and it allows you to refer to a bunch of implied variables in GitHub, and this will then be replaced there. The vulnerability here is that it uses the pull request title, and that's being sent to a bash variable called title. But there's no escaping here, no validation. So if some adversary would introduce a pull request name which contains a double quote, that double quote would end the string literal that's being assigned to the title, and whatever comes after that will be assigned as bash code. Right? So this will allow the creator of a pull request to execute arbitrary bash code in the context of your workflow. So it's a vulnerability of the workflow per se, and just like SQL injection is never like a problem with SQL, it's a problem with the language that invokes SQL. This is not a problem with bash, this is a problem with the GitHub workflow syntax that invokes bash. Right? That's just one example of what can go wrong and everything is good. So we're going to look at this topic a little bit more in depth. When we start with looking at SAST technology in its current state a little bit more. Like how does that actually work? What can it do well? How does it work under the hood? Because that will allow us to better understand why everything as code is special for SAST. And then we're going to look at two languages like as case studies for this general phenomenon. First one will be Bicep, the other one will be Solidity. Looking at SAST technology, there are many different tools, right? As we've seen, Fortify is just one of them. How they all work, they take some input, and then as a first step, they transform that to some intermediate representation. So you generally do not do the analysis directly on the input. And the core reason for that is that all SAST tools, all practical SAST tools have the ambition to support many different languages. So there are dozens of languages that companies use and want to see analyzed using SAST. And you cannot write your analyzers for all of them individually, right? So you need to have some form of normalization there. And then you do the actual analysis and that leads to the results. There are many, many different areas where there are tool-specific variations, where one tool is not the other one. Now, it's not in the scope of this talk to discuss all of them, but I want to zoom in on one of those things, the algorithms. That's going to be the key thing for the rest of the talk. Now, let me start with a very boring SAST algorithm. So structural analysis. So we do have that on board in our tool, and all major SAST tools have that on board. And it just looks at the structure of the program and tries to look for vulnerable patterns. And here we see two examples. So the first example, 125, we have a hard-coded password, right? String password equals super secret. The way SAST would recognize that is that we see that a string literal is present, so string literal being super secret, and that string literal is being used to initialize a variable that is called password or key or something. So that's a very solid indication that you're dealing with a hard-coded password. Also a very simple algorithm to implement. Problem with that is that reliability tends to be really poor, and you see that in the other examples, right? So on the first line of the second example, you see a typical false positive for this type of rule, right? Where a password is being used to describe some kind of prompt that you're going to give to the user, but it's not the password itself. Any human can very easily see that this is not a hard-coded password, but SAST tools tend to produce a false positive. The second one, many complex SAST tools produce a false negative because the programmer has decided to use the Dutch word wachtwoord instead of password, and then standard rules will not apply. Right, so this structural analysis stuff is important. All SAST tools have it. It's also very, very, very limited. The actual thing, what SAST is all about, is this state analysis. So here we see some more advanced example. This is a piece of vulnerable code written in Java where we have a Spring web application that makes a connection to the database, and there's a SQL injection present here. So it's over two files. The reason why the SQL injection is present is that on the first file, the top half, you see that we are getting some request parameters, and based off all those request parameter annotation, so the thing that starts with the @ sign, we can know that this is actually map input, because that's how Spring handles things. This is then being used to invoke the post method in another file, which then goes to the database via JPC, by Spring Studio C facility. You see the string concatenation there, so the input from the user gets concatenated with fixed parts. This is well known to be susceptible to SQL injection. So this is something that SAST tools generally find without much difficulty, but you cannot find this using structural methods. Right? So you can structurally see, for instance, in the second half, that there is a SQL statement being created through concatenation, which by itself is suspect, but that's still not a clear sign that there is an actual exploitable vulnerability. You can only know that if you know that there's actually user input go into that string concatenation. And that's something that you can find through taint analysis. So the way these algorithms work is that we identify these parameters that have been annotated in the first half as so-called sources of taint. Then we track how that taint propagates through the program, through function invocations and through assignments and through constructs or functions that pass through taint. And then we see how that taint sinks into that JDC template execute method. And that's a very, very reliable way of finding issues. Right? So this is the core of the SAST algorithms. If you look at Fortify, roughly 75% of all of our rules is for this type of analysis. There will be many other things as well, but this is the core of everything. And these are some examples that point out that there are some nuances here, some subtleties when it comes to that taint propagation stuff. So the first example here is about a case where we are leaking a password to the console. So the password gets printed to the console, which is a bad thing from a confidentiality point of view. And in a way, that's also a similar kind of taint analysis, right? We first see the source. We know that particular methods work in such a way that the password is being returned. And then that gets passed through the program. And then when it gets printed, then we want to flag that. But we need to track that separately from the other type of taint that we saw earlier, because otherwise, if we would treat any form of printing user input to the console as a problem, we would get massive false positives. So that's only a problem if it happens to be password or something confidential. So we need to make that distinction. We need to make a distinction between various taint flags. Second example is about weak cryptography. So here we're using the DES crypto algorithm to encrypt a password. That's not a good idea, right? It hasn't been a good idea for many decades. So SAST tools should reasonably warn against that. They see that in line 28, where we're creating a cipher, the cryptographic algorithm that we specify is not a literal at that point. Right? It's a variable that's being assigned earlier. So to detect this correctly, we need to understand what the actual value of that variable will be at that point once we hit line 28. Which means that we need to do a form of data flow analysis, which is not so much about taint, but it's just about understanding the values that things will actually have. And this is an area where commercial texts are on this topic and scientific texts start to diverge. So if you look at all of our commercial material in Fortify, also with the competitors, they will be talking about data flow analysis and then generally implicitly mean taint analysis. If you look at the scientific literature about this, then data flow analysis is actually a broader topic, which also encompasses this type of constant propagation that we see here. And that's going to play a major role in everything as going to space. If you think about implementing that, right, suppose that you're tasked with implementing something like Fortify yourself. That seems daunting, a bit magical if you've never looked into it, but actually there's lots of scientific literature about it. It's not a mystery. They're just like books that explain how that works. If you zoom into that analysis phase, that second phase after you've obtained the intermediate representation, the way it works is that we set up a control flow graph, which is essentially just a flow chart of the programmable decision points marked explicitly. If you have done that, you can start creating data flow equations. So they basically say for each block where you do not have a control flow jump, like what's true in the beginning, and then if we know what's true in the beginning, what's true in the end. And then you have a series of equations which you can solve iteratively. And there are some mathematical theorems that guarantee that this iteration actually converges, and that sort of things start getting a little bit hairy. But that's what you roughly do. And that's how all the tools work. There are all fundamentally different ways of doing it. This is an area, if you start to actually implement this is where some bias starts to creep in. That makes SAST tools perform well for things like Java and C and Python, what have you, and not so well for some everything is code cases. One of that is this entire idea of a control flow graph is highly biased towards imperative languages. Right? So languages where your programs are essentially a series of instructions. With declarative languages, your programs are essentially a series of facts or definitions. They behave differently. For one case, the order doesn't matter in that case. And that really has a big impact on SAST. The other thing is that the nature of that intermediate representation would very easily introduce all kinds of bias towards the languages. If you look at Fortify, our tool is about 20 years old. And it was created at a time where Java, C#, and C were clearly the most important languages to support. And what you see is that our intermediate representation, the specific one we have, is highly biased towards those languages. And then if you start to put new languages on top of that same intermediate representation, that starts to create all kinds of difficulties. And you can try to patch it and to improve it, but you never really fix that. The reason for that is that if you think about what should an intermediate representation ideally look like, it should be universal in the sense that all languages that you want to analyze nicely fit into it. But it also should be simple, because if that gets too complex, then your data flow analysis algorithm will be very complex. And it's impossible to satisfy all those requirements at the same time. Practical SAST tools, these IR languages tend to be biased towards situational cases. So that's a bit of theory. Let's look at it more concretely with some case studies. First one, bicep. So who here is familiar with bicep? So bicep is a language developed by Microsoft for infrastructure as code on the Azure platform. It's an alternative to ARM.json, so that's the other way in which you can do IAC on Azure with your JSON files. And bicep, in fact, compiles to ARM.json. You can also write ARM.json yourself manually. This is an example. I think this is maybe pretty small to read. It's not that small. So we have two versions here of the same thing. To the left, we have a bicep file that just deploys a storage account for a simple thing. The right-hand side is about half of the equivalent ARM.json. The rest didn't fit. And that shows the reason why bicep exists, right? To have much more condensed code. If you look at the security aspects of this, I think fundamentally they fall into two categories. So if you have infrastructure as code, then the infrastructure being created by your program may be insecure. And that's something that you won't come to detect. So a very classical example would be that if you create a server and there's no encryption on that disk, or if you open up port 22 to the world, that's also a bad thing. So that's the kind of thing that you could know of by looking at the infrastructure as code. There's also the situation that the template or the program as such may be insecure. And a very typical example is that you would be leaking secrets. Because IEC by its nature has access to credentials, keys. If you print them out to log in, it's that. To the right, you see an example where on line 8, you know that this parameter of passwords is a secure thing. In this case, you could know that just by its name password, but even if it had a different name, you would know that based on the decorator on line 7, which says that this is something secure, so it shouldn't be echoed to the console, etc. And then on line 10, we have a string interpolation function, so the variable credentials becomes the concatenation of a username, colon, and password. And then on line 12, that's printed. So that's the evidence here that this is a problem with leaking sensitive data. Now, let's look at some of the challenges for SAST, given what we just learned about SAST in general and how it works. Some challenges that you would face if you try to find this. So first of all, given that nature of how bicep and JSON work, this picture, it's really not good enough to just have a bicep. So what you need to have a bicep and ARM.json, so you need to understand how these two languages interoperate, because bicep code can refer to JSON code. The other thing is that if you look at the JSON case, you need to deal with what I call an encapsulated language. So it's a similar concept. So if you have the TCP/IP stack or the OSI stack, then you have IP packages. An IP package can actually be the TCP package. On the IP level, you wouldn't know anything about that. With all the TCP information is encapsulated in the syntax, it's all encapsulated in the IP payload. And here you see something very similar happening, but more on the language level. And so the example here is ARM JSON code. It's the ARM JSON equivalent of the sample that I provided where a password is being leaked. On one level, this is just JSON data, right? And JSON data as such would be very uninteresting from a SAST perspective because there's no semantics or data flow or anything. It's just data. But if you look at this carefully, you see there was actually another layer where there is an actual program, right? Where you define parameters. On line 26, you see string interpolation happening. And then on line 30, you see output happening. So there is this kind of data flow thing that you need to understand as well. But you can never understand that by thinking about this just on the JSON level, right? It's encapsulated within the JSON, it exists somewhere else. So just making a SAST to support JSON is very simple, we've had it for years, but it does not allow us in any way to detect those types of things. You need to have different mechanisms. Third thing, you need to understand the declarative nature of this, and this is really counterintuitive to many people. If you look at the program here to the right, it's again a variation of that password leak program, except that everything is reversed, right? So now we start with the output on line 3, and then we do the string interpolation on line 5, and then we have the parameters. This program is semantically equivalent to the one that we saw earlier. There's no difference at all, because it's all just decorative. If you naively try to apply SAST techniques to a program like this, results will be very different, right? If you try to do the taint analysis thing, then if you first assign taint to a variable and then use that variable in the sink, that's rollable. But the reverse thing, it's not rollable, because then you would assume that once you hit the sink, the variable hasn't been tainted yet. That is completely valid reasoning in imperative languages like Java. It's not valid in this context. So you need to have some solution for that as well. And then finally, the constant propagation thing, which is a bit of an edge case for things like Java, for the DES algorithm that I saw earlier. That becomes crucial here because almost everything that you want to find in terms of infrastructure being insecure has to be found by analyzing the concrete values of large complex JSON objects. So let's look at the second case, solidity. Anybody familiar with solidity? Anybody here writing smart contracts? One person, great. Need to have it here tonight. So solidity is a language for writing smart contracts. So smart contracts are like fully automatic contracts that live on the blockchain, primarily the Ethereum blockchain, not on the Bitcoin blockchain. There are a couple of other blockchains, but practically it's about Ethereum. Think about it like this. So if you have a traditional blockchain with Bitcoins or anything, they allow you to have one operation, and that single operation is to send funds to someone else. So that's what we support. Smart contracts are a vast generalization of that. They allow you to do many other things as well. So instead of just sending money, you can make commitments to, for instance, have a form of insurance. So one example would be that suppose that you have an ice cream shop, right? And an ice cream shop only makes money in the summer, generally speaking, and it's dependent on the weather. Right? If you have a very rainy summer and no one's at lunch and you're never sure, then your ice cream sales will not be great. It would be nice to get insurance against it. And there are in fact insurance companies that offer things like that. Like if the average temperature is below so many degrees, you get some money. But with a smart contract, you could fully automate that. So there are companies that feed data about the weather to the blockchain, so you have access to that. And then if you have a smart contract that gets deployed, then the insurer will be able to upfront transfer money into that contract. And then if the actual weather becomes less than the agreed upon threshold, then it will be automatically transferred to the insurance holder. If it doesn't, it will automatically be funded back to the insurer. Similarly, you could set up auctions, all kinds of things to get fully automatic contracts without any trusted third party being necessary. Technically, this starts with Solidity source code. which gets compiled to EVM bytecode. So EVM is the Ethereum virtual machine, and that's the virtual machine that runs as part of the Bitcoin, the blockchain transactions. So this may all sound a bit abstract. This is like the hello world of Solidity smart contracts. And so it's a bit like Java, except that instead of classes you have contracts, and the act of deploying a contract to the blockchain is kind of like instantiating the classes in an object-oriented language. And here we just have a single field which says hello world. Interesting fact about this as well is that it specifies the exact version of Solidity that is applicable to this contract. So this wants to be compiled with 0, 13 or higher, but not anything else. Let me skip some of the details about this here. This is a somewhat more interesting example. So here we have a smart contract which only has a counter, so it's still not useful. It's still like a hello world type of example, but it gives you a little bit more impression of what can be the smart contract. So here we have a couple of functions, which are the equivalent of methods in normal object-oriented languages. And these are the things that can be invoked as part of the transaction. So whenever you interact with a smart contract, it's always about calling one of these functions and optionally also sending money to them. In this case, there is just an increment and decrement function where you change your counter. And you can also get the value of the counter. Completely interesting, and it's just to give you a bit of a flavor of our code, like Solidity code looks like. It's not complicated, it's something that you can get started with very easily. Now, if you think about why I care about this from a security point of view, intuitively, I guess it's clear this is about money, and potentially large sums of money. But there are also many examples of funds being stolen because of application level problems on those smart contracts. I have a couple of links here. If you want to them yourself, you can correct what news is very interesting. That's new cases every week. And often it's about millions of dollars, sometimes hundreds of millions. So there's a big security is very much at stake here. If you then think about what is that, what would be the OWASP top 10 for smart contracts? There is no OWASP top 10 yet. There is something called the SWC registry, which kind of serves that same purpose. It's a list of 39 issue categories that are now included in more formally specified standards. That's the best starting point if you want to understand the type of vulnerabilities here. I'm going to pick out two. So the one is called authorization through TX origin. This outlines why that is a problem. Of course, in a smart contract, it often makes sense that you want to do some form of authorization, that you want to know whether the people who is interacting with you, and in particular, whether you're dealing with the owner of the contract or with someone else. So Solidity has a bunch of implied variables, global variables that you can use for that purpose. And there are two are relevant here, TX origin and message sender. Now, in the simple case where someone directly interacts with a smart contract, these are the same. They have the exact same value. They both hold the value of the person initiating the transaction. The problem is that once a smart contract calls another smart contract, which is possible, very common, then they start to diverge. And then TX origin is the original entity starting the transaction, and message sender is just the last hop. This is something that an attacker can exploit. So if you have a wallet contract, so some that is held by some owner and funds should only be obtainable by that owner, and if that wallet contract happens to be using TX origin instead of what it should do, which is using message sender, the vulnerability can occur. In that case, an attacker can deploy an attack contract, can then make the victim through some phishing attempt do some interaction with them. It might be about a very small amount of money, it really doesn't matter. But at that point, an attack contract can call the victim's wallet and can do whatever they want with the user's identity, right? Because at that point, even if that attack contract contracts the victim contract, then message sender will be the attack, but TX origin will be the identity of the victim. And so then the attack contract can act on behalf of the victim and withdraw all funds. As live examples of all this running on my laptop, there's no time in this presentation to to show them if you're going to see that data. And here you see a concrete example of what vulnerable code looks like. You're on line 16, you see the authorization check. So we verify whether TX origin equals a preset owner. Result of that boolean goes into the require method, which generally determines if a Solidity transaction may proceed or not. But this is wrong. Right? This is explained. It should say message to sender and it'll be fine. Second problem is reentrancy. So reentrancy is a major source of Solidity weaknesses. Reentrancy is also something we know of in general application security context. And then it has usually to do with multi-threading, with time of check, time of use, those types of things. And Solidity is very different. So Solidity, because it's part of a blockchain and everybody needs to be able to verify, there's no room for non-determinism. So it's a fully deterministic environment. There's no multi-threading or anything like that. So it's a very different style of reentrancy problem. This is an example illustrating it. So here we have what's called a metacoin contract. So it's kind of like a small bank living on the blockchain, where several owners can have, or several account holders can have particular balances. And then on line 16, you see a sell function. The sell function is for someone who holds funds into this account to sell them and to use them for something else. We see three things happening. We see a test whether that person that wants to withdraw money actually has the balance, right? That's what your bank will also check before you withdraw funds. And then we see that the funds actually get transferred. That's the second thing there, the interaction. And then we see that your current balance gets updated, right? Just to record the fact that you now no longer have those funds. Makes perfect sense. Seems safe. If you would have a traditional database with asset transactions, would be completely safe, right? Because either the entire thing would work or the entire thing would not work. In Solidity, this is absolutely not safe. And the reason for that is that an attack contract may be necessary. So the attack contract may receive that payment as part of the interactions, and then it could again call the same contract. So you get a loop. And that's the reentrancy part. And then that loop would hit that require instruction again, so that the test, but at that point the balance hasn't yet been updated. Right, so it still sees the balance as if no transaction has taken place yet. So you enter this loop, you can actually drain the entire contract. The way to protect against this, there are multiple ways, but the key thing is to reorder your actions here. So you also always should have the checks, then the internal updates, and then the interactions. Interactions should go last, and then you're not vulnerable to this problem. It's a very Solidity specific thing. If you think again, like what does a SAST tool have to solve here? A couple of really interesting things. So if you look at that TX origin case, so the first one, as a SAST engineer, like my first reaction to that is that's a taint problem, right? It's just a new taint flag. I somehow need to keep track of TX origin as a source of taint. Then I see that flow into a require directive. That's a problem. So require is the same, TX origin is the source. And that seems to make sense, but it doesn't work. The reason it doesn't work is that this type of taint flows through a binary form, right? So we compare that TX origin with something else, with a preset values. That is a yes or a no. And then the require sees that yes or a no. So the taint flows through that binary. Normally speaking, taint cannot be even Boolean, because taint as a concept generally represents some kind of attack payload. And a Boolean value, just one bit, that's not enough to contain an actual attack payload. So if you look at the above example here to the right, we see an example where we start with taint in Java, but then we get that taint into a Boolean form, and then print that Boolean again as part of a SQL statement. And in this context, that conversion to a Boolean is actually a technique to validate the taint, right? So this is not vulnerable because we convert the taint to a Boolean. So Boolean cannot carry taint in that case. But in the equivalent Solidity case, a Boolean can absolutely carry this type of taint. So it's not really taint, it's a different type of thing. So we need to have very specific so-called propagation rules. There's some flexibility there to recognize that there are things that are taint-like, but not quite like taint. Second thing here, if you look at that second problem, with that order of actions making a big difference. The key thing there is that it's fundamentally not a data flow problem. This is a so-called control flow problem, which you need to model as well, but you cannot use the exact same techniques here that we normally use. Some conclusions. So if you look back at that space of SAST and everything is code, so is SAST relevant for everything is code? Absolutely. Right? There are many security problems that can occur in everything is code. We saw it with GitHub, we saw it with Bicep, we saw it with Solidity. We could have given you many more examples. So we need to look at that as a security community. Even though OWASP was called application security, it's not like there's an other everything is code community. It's going to be up to us to also look into this space. We also see that with our customers that have once acquired Fortify for application security, are now just saying, hey, I actually want to use Fortify to scan all my code, so that everything is code stuff is definitely in our domain. So our SaaS tools now doing a good job at this, generally no. Most SaaS tools, including ours, have something, but it's not fantastic. It's not, in many cases, the infrastructure as code coverage is based on looking at data alone, but fails to grasp that data flow stuff that takes place as well. If you look at what kind of things SaaS tools need to do to better deal with that everything is code scenario, it's not just about supporting more languages. More things are needed, right? We need more support for declarative paradigms. We need to understand that language encapsulation thing that we saw with RNJSON, but for which many more different examples exist. We need to have that advanced tunability of what we mean by taint propagation and be able to express that in Solidity. Taint may actually fly to a Boolean value. Many different things to do here. So that's the end of today for this lecture. I will be here for the entire day to know more about Fortify or about see those smart contracts being hacked live. We can do that. Also, I did not talk about AI, which is a topic we're working on a lot in Fortify. So both using Fortify to detect AI risk, but also using AI inside of SAST for better detection. So we want to have discussions about that later today. That's it. Thank you.